going over example 5A3 in the textbook. What we're given is a bicyclist travels to the right as she brakes. In one situation, she brakes with only the rear wheel. In another situation, she brakes with only the front wheel. Comment on the possible differences between rear wheel and front wheel braking as viewed from a dynamics perspective. So here you can see I've drawn the bicyclist. We're going to the right. The distance here is labeled from the front brake to our center of gravity, as well as the rear brake to our center of gravity, and then the distance between the ground and the center of gravity as well. So starting off with step 1 and 2, pretty simple. We're going to draw our free body diagram as well as the coordinate system. So starting off, we just want to make a coordinate system, simple I and j hat, as usual. Now for our free body diagram, we're going to have 5 forces. One acting downward due to gravity is our weight force. Right here, just going downwards, and then we're going to have a normal force on each tire as well as a friction force for each tire. So here you can see I've labeled friction F with a subscript B for the rear tire, normal force for M with a B for the back tire as well, and then our forward tires both have subscript of F to keep the forward tire straight. Okay, so next, now that we've got our forces from our free body diagram, we need to label our forces in vector form. So starting off with the rear tire, we've got our friction force as well as our normal force. Those are the friction force is acting in the I hat direction, normal force in the j hat, so we can simply just label those as negative F B I as well as a positive NBJ. And so it's going to be the same thing for the front tire, only this time subscript F. Now, of course, we need to label our weight force, which is going to be a negative mass times gravity in the j hat direction, since the weight force is acting downward in the j hat direction. Now for our acceleration, we've only got one acceleration direction since we're not going upwards. We're simply just going to the right, so we're only going to have acceleration around center of gravity G equals acceleration of center of gravity x I hat. You don't have to worry about a y j hat direction because we're only, again, going in the right direction. Okay, now that we've gotten our accelerations and our forces written out in vector form, we can now use a sum of the forces equals mass times acceleration for step 5. So now all we're going to simply do is take our mass times our acceleration here and then sum our forces. So writing this out, we're going to have our negative FB I hat, negative F front I hat, minus our weight force, plus our normal force in the rear wheel, as well as plus our normal force for the front wheel. Now we're going to set that equal to mass times our acceleration here. So it's just simply going to be mass times acceleration x I hat. Now using this equation, we can break it off into our 2 scalar equations for I and j hat. So I hat, simply just going to take all of our I hats out of this equation and set them here. Now this is what we end up with here. And now we do the same thing for our J hat. Now, as you can see, the right side of this equation is going to equal 0. That's because our acceleration does not have a J hat direction. And then here, all we did was take our normal forces and our weight force, since they're in the J direction, put them in this equation. And then again, recapping here, we got our two I hat forces, and then we multiplied our mass times our acceleration in the I direction, and set them in this equation, taking them out and putting them in the I and J hat direction equations. Okay, so starting step 6 here, you can see that we are ready to now move on to our sum of the moment equations. Using special case 1, we can see that this is the equation we get. Special case 1 just says that you can put point A, or any point, on our center of gravity, G. So using that, we get this equation. However, our system here is not rotating. We're only going one direction, so our alpha here is going to equal 0, which means our sum of moments is going to equal 0. Now, summing the moments, we will get, using these distances here from earlier, this is what this is going to look like. So we take our normal force times our brake force here in the front direction for both the front direction of the tire, the front brake distance, as well as the same thing for the back tire. And then we take our friction force B times the distance. Okay, so now looking back at the actual question we're trying to answer, we have to comment on the potential differences between the rear wheel braking and front wheel braking. So now looking at the back brake, we've gone through our 6 steps, so we know what we're doing now. Using back brake, the force of the front brake is going to be 0 here since we're only using the back brake. Now labeling the force of the back brake, we're going to have mu k, so friction of kinetic energy, times the normal force of the back wheel. We can derive this trying to solve in the end for the acceleration of G in the X direction. So now deriving this equation further, we've got these two equations here that we can use to continue solving the problem. So moving on, we can simplify it. This is what we're going to get. We're going to get mass times acceleration G in the X direction is equal to mu k times normal force B. Now the normal force in the F direction is still going to equal mass times gravity minus normal force in the B direction. We got to keep that in mind. We derive that using our J hat scalar direction equation. So now continuing to integrate all of our equations here, we're going to get this equation, which we can continue to work towards our end goal of acceleration G in the X direction. So now solving this through, we get our normal force B is going to equal mass times gravity times the brake force direction, the front brake distance, sorry, is over divided by our distance in the front brake, distance in our rear brake, plus UK distance D. Now integrating all of these equations to solve for our acceleration in the X direction, it's going to give us negative mu k, because we have to keep in mind the friction is going to be a negative direction, times mass, times gravity, times distance of front brake, divided by mass times front brake distance plus back brake distance plus friction force times D distance. Simplifying this, we're going to get our acceleration in the X direction using our back brake is negative mu k times G times front brake distance divided by our front brake distance plus our back brake distance, as well as plus mu k D, because here our m's would cancel out. So starting out here, now we're going to do the front brake analysis. We just did the back brake analysis. We have that equation written down there so we can compare them later. So previously we used the back brake with its equation and the front brake being 0. Now we're going to flip-flop that. The back brake's going to be equal to 0. The front brake's going to be equal to friction times the normal force in the front. So using the set of equations here, we can, like we derived the back brake for the solving acceleration, we're going to do the same thing using the front brake. So solving through, we've got these two initial equations here that we can solve using a system of equations. So deriving this, we're going to get the normal force in the back is equal to mg minus this normal force here. Similarly, we're going to get the normal force times the front brake distance is equal to normal in the back times distance in the back minus the friction force, normal force F, times the distance d is going to be equal to 0. We've derived that equation using our step 6 sum of moments. And again, there's no rotation in the system, so that alpha is going to be 0. And that's where we're getting this equation from here. So now solving this through, we can combine the equations. We're going to get this long equation, solving for that normal force in the front direction. Separating it out, we're going to get mass times gravity times distance from the back brake, all divided by distance from front brake plus distance back brake minus friction times d. Now solving for this acceleration, just again going through system equations, we're going to get negative friction times mass times gravity times the back brake distance divided by mass times back force, front brake distance, sorry, rear brake distance minus friction times d. And then again, similar like the back brake equation, we can cancel out our mass, and we're going to be left with negative friction times gravity, distance to the back brake divided by front brake distance plus back brake distance minus mu k times distance. So here we can finally answer our question, which brake will create a larger acceleration. So as you can see, we're braking, so we're stopping negative for the negative I hat acceleration. So here, key differences we can see is the distance to the back and distance to the front. Here we can see the distance to the back is going to be larger than the distance in the front. The problem doesn't give any given numbers, but we can see just using the picture, this is going to be a longer distance than the front brake distance. So using that, we can see that this is going to have a larger numerator than this number. The other key difference is here we are adding the mu k times d. Here we are subtracting. So that means we're going to have a lower denominator, larger numerator as compared to the back brake. So if we're getting a larger numerator, smaller denominator in the front brake, that means that the front brake is going to create a greater negative acceleration. You're going to be able to brake faster. Thank you.